is the right one?
That looks perfect.
Okay, sorry.
All right. No, you're fine. I'm so sorry to interrupt you. Go ahead.
Okay. Um, so to start off, let's look at current electronics. If we think about the evolution of electronic devices over the years, it's really obvious that society as a whole has been pushing for electronics that are faster and more powerful. If we look at computers today, it's easy to tell how much of a difference there is between them and computers from 10, 20 years ago. But a big issue with developing better electronics is the large energy consumption and difficult thermal management. This can be seen in day-to-day life with just how dependent people are on electronics. The energy consumption is very large. Um, and so one side effect of the large energy consumption is that carbon neutrality is seemingly impossible. At the rate that we're progressing in electronic development, climate change and other environmental issues will become harder and harder to prevent. As such, we're looking for alternative ways of data transportation so that the demand of energy can be reduced. So to first understand antiferromagnetic nanostructures, we should start with its foundational concept. So what exactly are spins? Spins are an inherent property of elementary particles. That's to say, rather than a tangible property like how massive something is or how fast it's moving, it's more comparable to angular momentum in classical physics. And so this property affects how particles interact with magnetic fields. An important part of spins is that they are quantized, meaning they can only take on specific values. For example, electrons have a spin of 1/2. Here on the left, we have a diagram of a spin, and on the right, we have a diagram of spin waves. So now that we know what spins are, how can we use them? Right now, most electronics operate through the movement of electrons, which I've already mentioned use a lot of energy and tend to overheat. The fact that phones and other devices tend to heat up when we use them a lot shows how much energy we're wasting. You get heat out emitting from your electronics rather than using them for like other things that we use electricity for. And so that energy is released due to how fast the electrons move. Instead, we could be using that energy, and so we want to replace the current energy inefficient way of moving electrons, which we're exploring the use of spins as a method of information transport instead. So how can we put this knowledge into practice? Right now, there's already research into the usage of ferromagnetic materials. Here on campus, we're doing research into antiferromagnetic materials instead. The reason for this is because they have a much higher spin wave excitation frequency. Ferromagnets tend to operate in frequencies in the range of gigahertz, while antiferromagnets operate in the range of terahertz. So we could have up to 1,000 times faster speeds than what ferromagnetic materials could produce. As a result, we expect devices that use the technology developed for antiferromagnets to have much greater operational speed, as well as less energy consumption than the current standard of information processing. There are some complications in this research. With how we currently measure spin excitation, we would need to put samples under very, very specific conditions. We are using a cryostat to generate cryogenic temperatures and very high magnetic fields. The machine that we currently use goes up to 7 Teslas. A picture of the chamber in the cryostat is on the left, or on the left, we can see a picture of the cryostat, and we can also see the sample pod, which is indicated by the color yellow. So using inductive microwave spectroscopy, we are testing antiferromagnetic samples. One of these samples that we have in the lab is shown in the middle, which is chromium oxide, which we would put in the sample pod and then into the cryostat. From this, we plan to move towards optomagnonics, since measuring spins at high frequencies require optical elements, like lasers and things like that. On the right, it shows the basic process of how it should work. By using spin pumping, we generate a spin current, which we can then measure with the probe. So here are some pictures of the cryostat in our lab alongside the devices that we use for our measurements. There are some microwave sources and spectrometers, as well as low frequency current sources, nanovoltmeters, and lock-in amplifiers. On the right, there is some data that we've gotten from our samples. Here, the different colors in the graph show the different frequencies we've tested for samples. You can see definite peaks in voltage as we set the magnetic field to specific values, specifically 50,000 and negative 50,000. Current electronics process data on the moment or the movement of electrons, which is essentially voltage. Since we're able to get voltage readings without having to move electrons, this seems like a definite possibility for a new method of data processing, although it might be a while since we see it in actual use because of the constraints of requiring low temperatures and high magnetic fields in order to get the frequency that we want. Here in the top right, you can see the sample plot for the cryostat that I pointed out in the diagram. It holds the chromium monoxide sample that we prepare. And so then on the bottom, or on the left and the bottom right, we have the electrical breakout boxes, which we're using to interface the cryostat with the other devices I mentioned earlier, like the microwave sources and spectrometers. Part of my research project was soldering these boxes, which essentially is soldering on the 8 BNC connectors on each box. These boxes allow us to get signals from the cryostat, which we can then record the measurements using the measurement devices. So with that in mind, what are some potential uses of these spin-based electronics? The first application we could use this for is spin qubits for quantum information. With this technology, we would be able to have energy efficient and faster information storage and processing. We could also potentially use this research for neuromorphic magnetic networks, which has potential applications in fields such as artificial intelligence, machine learning, and more. Since these magnetic materials exhibit non-volatile behavior, they can retain their state even when power is turned off, which means, once again, we can reduce energy consumption from traditional methods of computing applications. So I would like to give special thanks to the Barsukov Research Group, namely Professor Igor Barsukov, as well as the graduate students Shrash Remy and Runong Jiang, as well as the UC Riverside Undergraduate Education Mini Grant Program. Here are some references. Thank you all for listening. Are there any questions?
All right, wonderful. Thank you, Audrey. Do we have any questions for Audrey? So Audrey, I have a question for you. And I have to be honest that this is not an area that I know very much about. So I'm hoping that this question makes sense, but you can tell me if it doesn't. But I've heard a lot lately about, the advances in battery storage and how that's made a lot of other devices more sustainable or increased our ability to sort of have more efficient electronic devices. So does this relate to that kind of work at all, or would it be used in the same applications, or this is just completely something separate and really focused on like electronic devices like computers and things like that?
Yeah, I think as far as I know, this is more about like directly how electrons like circuits, for example.
Mm,
For if you try to like turn on a light, for example, right? You have electrons moving through wires, and so the wires will heat up because the electrons are moving. And so that's essentially what we're trying to circumvent, is that we can stop wasting energy in that way where instead of heating up the wire, we want to make it so that the light bulb will like stay on for longer.
mm.
Instead of like you were saying, batteries, it's kind of like it would be able to be used in tandem, I would assume, with this type of stuff.
That's a great explanation. Thank you. I see what you mean by that. The two could maybe live together. Okay. Macy.
Thanks, Britt. Thank you, Audrey, for that presentation. Can you share, are there other countries, or how does the US stand in terms of spin-based electronics? Are we kind of in the middle, at the forefront? Are we kind of behind? And who in this world is sort of paving the way in these kinds of electronics?
I am not sure about these statistics. I'm sorry.
That's okay. Maybe I'll look it up later, but this is very fascinating. Thank you.
All right, wonderful. Okay, well, join me again in thanking Audrey for her wonderful presentation. Thank you so much, Audrey, for your work and sharing with us.